It's F4. And then just bring it close to the camera.
Okay.
Wow, your internet is very choppy, huh?
Yeah, I'm in my room.
Okay. The actual interview itself, you need better internet than this. Otherwise, it won't work. Talk to Charles if you get an interview, and then usually be able to arrange one at the school. With a much better internet.
Okay.
Okay, cool. SF4 then.
Yes. Let's see.
Okay. Yeah. Did you just draw it as like single electron and single electron on the
Yeah.
sulfur? What
Single.
does that mean? Where did you learn that? You just talk about pairs of electron, right? You have two unpaired electron. That makes you one lone pair. They don't go like that at all. Okay, they stay as a pair. Okay, when they stay as a pair, can you think about your bonding pair and lone pair repulsion? So your bonding pair are currently 90 degrees to each other, right?
Yeah.
Okay. How about your lone pair to your bonding pair? What angle is it at?
Also 90.
Also 90. So when you think about it, lone pair to bond pair, how many do you have? You have 4, right?
Yeah.
And then
Bond.
bond pair, you also have 4. Do you agree?
Yeah. Yes.
Do you think that is the optimized geometry with minimal repulsion?
Nope. Sorry.
I'm gonna show you something, and then this is actually the correct answer. This is how SF4 is going to look like. Can you see?
Yeah.
Can you visualize the geometry?
Yeah. The lone pair
Okay.
is
If you draw it on your paper, and then I'll take it away, then we can discuss it. Done? Okay. So this shape is called a seesaw. Do you know when you do a seesaw, it's like you have a plane, and then you have that one in and one out support. Okay. So
yeah.
again, can you count the bond pair and bond pair? So there are 4 bonding pair there. Okay.
Yep.
What angle are they at? They are each at 90. Hang on. They are not all at 90 degree anymore. Do you agree?
Yeah.
So there's the axial and then there's the equatorial one. Let's call the up and down as the axial. So the axial and the equatorial. So you got bond pair and bond pair at 90 degree. How many of that do you have?
Bond pair.
So it's like yep, the up one can go to the in and can go to the out, and then the down one can go to the in and the out. Right? So those are at 90 degree. How about the one in the middle?
120. You mean the
Yeah.
equatorial one?
Okay.
There.
So what did we say about the valence shell electron pair repulsion theory? We said that bond pair will repel less than bond pair lone pair, right?
Yeah.
So essentially, when you have a lone pair, they are not bonding, and therefore they protrude more out in space, like you said, and therefore they will repel more with the bond pair compared to the bond pair which are localized. Well, all of them are localized, but the bond pair is more localized because it's fixated in place. Cannot do anything at all, right? So
Yeah.
can you see the lone pair and the bond pair now? The lone pair and the bond pair on the axial position is still 90 and 90. Agree?
Yeah. Yep.
So there's 2 of the lone pair and bond pair at 90 degree. Okay, there are
Yeah.
2. And then what about the lone pair and the bond pair on the equatorial position? What angle are they at?
Should be slightly greater than 120.
Yeah, around 120 degree, right? Close to that. And you have 2 of that, the one in and the one out.
Yeah.
When the geometry that you have given me just then, the the lone pair and bond pair, you have 4 of them at 90 degrees each. So what do you think? Which one is better actually? So based on what you know about lone pair and bond pair repulsion, so they will repel more, right? If they repel more, they want to stay further away from each other in order to have an optimized geometry. So which geometry is better, the seesaw or the square planar?
Seesaw, because if
Can
the
you see
lone
why?
pair, yeah,
Yeah.
if the lone,
They have at least the lone pair and the bond pair, 2 of them, 2 pairs of them further away from each other compared to like all 4 at 90 degrees. That's not the optimized geometry. They can still get further away. Yeah. Okay. And when you can get further away, why don't you get further away? Because optimized geometry means your standard structure is more stable at room temperature and pressure. Yeah. Okay. Seesaw. This is a very common one. The seesaw is a very common one that many people don't know, and they like to ask it in an interview somehow. What about IF5? What can you tell me about IF5? Do you want to draw me what do you think about IF5?
see.
Actually, start for me at IF3 first. Start IF3.
Okay.
Okay. What have you got for me for IF3? Come on, tell me what you think.
I'm still enjoying it. So near this.
Why do you think that is? Why not trigonoplanar?
Because idea is lone pair still. So the lone pairs
So you've gotten to it. So do you actually know the answer beforehand, or do you know it, or you just figure it out or something?
it should be trigonoplanar because.
But you didn't draw trigonoplanar, right?
Yeah.
Why did you draw what you draw? Come on, tell me why you drew that.
2 lone pairs on acting on one bonding pair, but then if I did it on the axial, then it would be acting on 3 bonding pairs, but then the bottom lone pair would cancel it out.
They won't cancel it out. In fact, it would have like, if you think about the top one, if it is trigonoplanar, top and below, the axial position will have like almost like 6 times the lone pair bond pair at 90 degree. And actually what you drew was actually correct. The trigonoplanar shape, which is what most people would have gone for because they thought they would cancel out. But it doesn't exactly cancel out. It's a repulsion. We are not talking about cancellation. It's not a dipole. It's not a dipole, okay? Okay, we are not talking about dipole. We are talking about the strength of the repulsion. So whatever you drew there without the lone pair, it actually looks like a T shape. So remember, you don't actually see lone pairs. So what you see is like a T shape. Can you see that?
Yeah.
Yeah, okay. So that's actually a common one that they like to ask in an interview as well, okay? And going from, IF to IF3, and then they will go to IF5. What do you think about the IF5? Come on, you gotta speak up when you do this kind of Skype interview. Yeah? Otherwise, it will be like a lot of silence with the interviewer waiting for you. You need to be able to talk while doing as well. That's what I meant by talking out aloud, thinking out aloud. Okay?
Yeah.
So,
Um,
you think IF5 will look like that?
Yeah.
Okay. Can you justify it? Why not? Why not the? Why not 5 of the fluorine like pentagon and then a lone pair? Why not? Why not that? Why do you go for this one?
The fluorines, if 5 fluorines in the same plane and then one lone pair above, then the fluorines would repel each other, and then the lone pairs would also repel on 5
Okay.
fluorines.
Well, we know the bond pair will definitely repel each other, right? But they repel less than the lone pair bond pair. But again, the question of fluorine comes down to the small size of the fluorine. The small size of the fluorines also means the bond is going to be quite short. You know, like how when the bond pair are short, then you have atoms that occupy space, and then they're going to repel so much. They don't like it as well. Okay, so in this
Yeah.
case, because of the small size of fluorine, they don't like to fit 5 altogether. They actually like 4. And in fact, when you put the lone pair one down, or one arm, doesn't matter, and then basically one of the fluorine on the axial positions, you minimize the whole thing essentially. You have actually minimized the lone pair bond pair repulsion rather than 5 of them. So if you imagine if you have 5 of them on one plane, this is a VSEP argument. 5 of them on one plane and then a fluorine. So you have 5 times the bond pair lone pair. Whereas at 90 degree. Whereas when you have one fluorine, away from each other, there's one fluorine 180 degree from the lone pair, whereas you only have 4 now. 4 bond pair, lone pair repulsion, and hence you optimize the geometry again for minimal repulsion. That's the idea of VSEPI. Yeah? Happy?
Yeah.
They should be able to throw any example at you now. Like you should know your standard predictable stuff essentially. Anyway, what can you tell me about C part 1? What do you think? How do you think it will react? How AlCl3 will react with that diethyl ether, which is ethyl, oxygen, ethyl, and then also with chloride? What do you think? Are you still there?
Yeah.
Okay. Can we turn on the video again? Because I need to see how your how is the facial expression and stuff.
My video's off.
Yeah, it's not moving again.
Okay.
Yeah, it's moving again. So do you want to talk me through what you're thinking?
Wait, let me open the question actually.
I think we have like 10 more minutes to go. But anyway, let's finish this one off.
Yeah, let's finish it first.
So what do you think? What do you know about AlCl3?
AlCl3 is electron deficient. Would like to take. It would like to get an electron with Cl minus.
Okay. Do you want to show me how the end product is going to be like?
The details.
Don't be too fussy about drawing like the perfect diagram. Yeah? Essentially, once you draw something, show it to me.
This one is for where is it? Here.
Okay. Yeah, okay, cool. What you're missing is that the charge is now on the aluminium, and it's a dative bond, yes, and you should have shown the three-dimensional geometry. So what's the geometry about the aluminium now?
Should be tetrahedral.
So it's gone from what bond angle to what bond angle?
109.5.
What has been the change of bond angle?
From 120 to 109.5.
Okay, so tell me what you think it would do with that diethyl ether then.
The oxygen has a lone pair, so it could also form a dative covalent bond.
Okay. Do you want to show me how it's like?
The full structure.
Yeah. You can just draw skeletal for the CH2, CH3. I just want to see how is it about aluminium. Come on, sketch a bit faster. Yeah, all that. Okay, cool. What do you think the geometry about the oxygen is now?
It has one lone pair and three bonding pairs, so it should be trigonal pyramidal.
With what bond angle? So what is the change in the bond angle before it coordinates to the aluminium trichloride and after it coordinates?
From 104 to from 104.5 to 107.
What about around the aluminium? How has it changed?
120 to 100.5.
Okay, cool. All right. Actually, that's about it, really. I mean, the rest of it is pretty much okay, right? You know about the AlCl3 electron division, hence why it has to exist like Al2Cl6. Yep.
Yeah.
I'm just going to open up what Maimuna actually. She got an interview together with Aishi a few years, 2 years back, 3 years back, 2016, and they asked on shape of xenon tetrafluoride. What do you know? Can you sketch for me xenon tetrafluoride? So shape of molecule again, right? Okay. What do you think that shape is?
Square plane.
So why is this square planar?
That's where the fluorine.
Okay. How many bonding pair are there altogether?
4.
How many lone pair are there altogether?
2. Should be 2.
2 lone pairs. Okay. The next question is why doesn't the lone pair, why is the lone pair just like that? Why is the lone pair is what you have drawn above and below? Why can't there be, basically why is the shape is what you have drawn? It's the same argument we'll be talking about, right? The lone pair will repel the most. And in this case, you have got 2 lone pairs, and the best situation for it is for it to be 180 degrees from each other if you can. Any other possibility will give you lone pair at 90 degree, and that's not acceptable. Can you see that? Yeah, that's the basis of VSEPR. Yeah, okay. And we go on to another reaction called basically the same as the AlCl3 reaction just now. So you have AlCl3 plus Cl minus native covalent bond, right? Give you a complex structure like AlCl4 minus. If you have ammonia and boron, NH3 and BH3, do you think you can draw me how they will react? NH3 and BH3.
NH3. BH3 is electron deficient also, like,
Uh-huh.
I mean, yeah. So it could accept a lone pair from ammonia,
Uh-huh. Yeah,
form
okay.
a dative bond.
Yeah, okay. So what's the geometry about the nitrogen now?
From trigonal pyramidal to, I mean, from tetrahedral to trigonal pyramidal.
Sorry,
Wait,
for which one?
from
Let's talk about the ammonia first. Let's talk about the nitrogen.
ammonia
What's
used to be
Just tell
trigonal
me the
pyramidal.
change in bond angle. It's alright about geometry. Just tell me the change in bond angle. What was it before and what is it now?
Before it was 107. After it's 109.5.
How about the boron?
It changed from 120 to 109.5 also.
So both are now tetrahedral, right? Can you draw next to that an ethane molecule? An alkane, ethane. Alkane with 2 carbon.
Alkane with 2 carbon.
Okay. Can you see the similarity between the two? Yeah?
Quite.
Yeah? Okay. Cool. So you got both of them drawn out, right? So boron is 1 electron lesser than carbon atom because boron is to the left of carbon. Nitrogen is next to carbon to the right. So it has 1 extra electron than carbon. So if you have a carbon-carbon bond versus a nitrogen-boron bond, in the case of that complex there, right, NH3BH3 complex, you actually have an isoelectronic system. Total number of electrons are the same. 4 plus 4 equal to 3 plus 5. 3 outer electrons plus 5 outer electrons. Agree?
Yeah, agree.
Okay. Ethane is a gas at room temperature and pressure. Very, very, very low boiling point. By the time it's already at room temperature, it's already a gas. That thing there, NH3BH3, is a complex. It's a solid at room temperature and pressure. Can you guess why is that? No, actually not guess. Can you tell me? Can you explain to me why that is?
The nitrogen with the lone pair can form hydrogen bonding with the other molecule.
Really? What do you understand by hydrogen bond? By the time it forms that complex, that lone pair is used up, right? Do you agree? When you no longer have the lone pair of the nitrogen, can you even form hydrogen bond? So please do not say things just because you want it to be what you say it is. Okay, when I say guess, I actually means make an indicator guess based on correct and sensible chemistry. Can you explain to me now? Suggest what you think that is. So it's not hydrogen bond.
Yes, cannot. It doesn't have a lone pair anymore.
Okay. So we're talking about structure and bonding here, right? It affects the physical property. So a solid at room temperature and pressure means it has do you think it's what kind of structure is that NH3 BH3 complex?
That's true.
First of all, do you think so ethane has that sorry?
Ethane would be simple molecular, but then this one, since it's a solid, it's probably giant molecular. Or
You think iodine is a solid at room temperature and pressure as well? I2, yeah? It's a solid at room temperature and pressure as well. So the fact that it's a solid, does that mean it's giant molecular? Do you think iodine is giant molecular?
no.
But you said a solid, therefore it should be a giant molecular. What do you mean by that? That is a wrong suggestion to begin with, yeah? Okay. A carbon-carbon bond, it's not polarized, right? Because same electron negativity. How about this nitrogen-boron bond? Do you think it's polar?
Yeah, nitrogen is very electronegative.
So when you form this complex, what do you think the polarity will be like on the nitrogen and on the boron?
Nitrogen would be delta negative, boron would be delta positive.
Okay, and I can tell you that even though by intuition that should be correct, but it's the other way around. Why is that? Think about how you form it. How do you form it?
Nitrogen donated its lone pair to boron.
Okay.
For the
So which one has actually gained the electron?
it's the bromine. I mean, yeah, it's the boron.
So which one do you think is actually delta minus now?
It's the boron because it
Because of the nature of the bond, you see. It's not a normal covalent bond. A normal covalent bond, yes, you are right. But this is not a normal covalent bond. This is a dative covalent bond. That's the biggest question of all. Okay. Do you know a carbon monoxide molecule?
carbon with triple bond.
Oxygen. Yeah.
Yeah.
Okay. Cool. Can you tell me the polarity? Can you draw me the dot and cross for carbon monoxide? That's the last thing we'll do. And then we'll talk about the polarity as well.
Okay.
Do you know the structure of carbon monoxide? So you know it's a triple bond.
There's a.
So I just want to see how you draw the dot and cross. I know CO is not in the A-level syllabus, but this is an interesting point of discussion considering what we just said actually. Problem with drawing dot and cross? See, I told you it's not easy to draw that dot and cross. Unless you know what you're doing. Have you ever seen the dot and cross for carbon monoxide?
Yeah, I think it unpaired electron and.
I will show you what it is like. Can you see this?
Yeah.
Do you notice what is special about it?
It's a dative bond.
Okay.
So.
Does the total number of electrons count alright to you?
1, 2, 3, 4, 5, 6, 7. Yeah.
Yeah, it counts alright to you. Okay. Tell me, carbon monoxide, right? When carbon monoxide poisons you, when you get carbon monoxide poisoning, it's a result of carbon monoxide replacing oxygen in the red blood cell. Because carbon monoxide is polar, oxygen is non-polar, carbon dioxide is non-polar, carbon monoxide is polar, is polarized, different electronegativity. So it likes to bind to iron 2+ in the red blood cell, in the hemoglobin. Okay?
Yeah.
If I have iron 2+, can you think about which side of the carbon monoxide, whether it's the carbon or the oxygen, would be the one that formed dative bond to the iron? So the structure I've shown you for carbon monoxide has lone pair on oxygen, has lone pair on carbon. Agree?
Yeah, it does.
So based on the structure that I show you on carbon monoxide, which you should know after today, how would it bind to hemoglobin molecule, or in fact any other transition method? I don't care whether it's octahedral or tetrahedral. I don't care. I just want you to tell me which side do you think it would use to bind to the metal center and why. Do you get the question?
Yeah, I do.
If you don't understand any question, you can always ask me to repeat again or ask the interviewer to repeat again. But what you should never do is just stay silent. You should have you started thinking? Come on, you don't need to get the right answer straight away, but it's important to think and talk through the thinking process. And sometimes talking through it, you can come to the answer. You can come to the sensible and rational response, which might or might not be correct based on your reasoning. At least when we can follow your reasoning, we can try and discover where you went wrong and try to guide you from there.
Yeah.
Okay, ready?
Sure, that's right.
Yeah. Which side?
Oxygen. oxygen pulls two bonding pair of electrons.
So
then-
you are saying that it will do something like this. So are you saying that oxygen will like to go for the iron instead of the carbon?
Yeah.
That's why. Yep. Okay. Cool. All right. Go on. What was your reasoning again?
There's two covalent bond, one dative covalent bond. Carbon. Okay. So that means carbon has its electrons and then 2 electrons from oxygen. But then for oxygen side, it has oxygen's 2 electrons, the lone pair electrons. And then it also pulls the 2 other bonding electrons towards itself. So oxygen.
But you're missing the big picture. When you want to form a dative bond to a transition metal center to form a complex, okay, you need to form a dative bond, right? To form a dative bond, you must have a lone pair, right? Yeah. In this case, you have a lone pair on the carbon, you have a lone pair on the oxygen. So both sides can essentially form dative covalent bond. Yeah. It's got nothing to do. Is the ability to do that has to do with the non-bonding electrons. Yeah, it's got to do with the lone pairs. It has got nothing to do with the bonding pair, which in this case, like you said, 2 covalent bond and 1 dative bond in between the carbon and the oxygen. That has got nothing to do with the ability to complex something because that's used up in bonding. Yeah. However, based on what we said about the NH3 and BH3, and you have fallen for this again. All right. So the dative bond inside the CO molecule is from oxygen to carbon. Right? So yes, oxygen is more electronegative than carbon, but because of this dative bond structure, oxygen is donating both electrons in that dative covalent bond towards carbon, right? So in terms of polarity, which the molecule is polar, which one is delta plus and which one is delta minus?
Carbon is delta minus.
Okay, and the oxygen will be delta plus based on what we said, right, about the dative bond. Now, in terms of forming the dative bond to the transition metal center to form a complex, do you think in terms of the 2 lone pair, one is on the oxygen, one is on the carbon, knowing the structure and the polarity of the CO molecule now, which side do you think will like to go for the iron, the carbon or the oxygen?
The carbon, because it's
because it's with the delta minus and not the delta plus, right? So in essence, you've gotten them the other way around. Okay?
Yeah.
Can you see why now?
Yeah, because the carbon.
So this is an idea about dative covalent bond, which you might not have thought about. Okay, just to wrap up, going back to that NH3 and BH3, so you got that partial ionic structure because of the dative covalent bond contribution. And when you have partial ionic structure, distribution of charges, it's not like in between carbon and ethane, it's just non-polar. Therefore, there's only when you have a polar bond like that, what do you have? You have a permanent dipole as well. Yeah, not only permanent dipole, but depending on like how strong it is, how strong the dative covalent bond is, you can essentially get like a partial negative charge on the boron, not on the nitrogen, because the nitrogen is donating a lone pair to the boron, and now you get a partial positive charge on the nitrogen. So this is also why amino acids can give you the Zwitter ionic structure. So in essence, you also have the simple molecular structure and the Zwitter ionic form. It's a similar kind of thing with the amino-boron complex structure, and that contributes to just more than van der Waals, which is what it is between the normal ethane molecule, and therefore it explains the more energy required to break this forces of attraction, and therefore why one is a solid despite it being isoelectronic. The term isoelectronic is to get people to confuse. Total same number of electron. Van der Waals should be the same, but you are assuming it's molecule versus molecule. You're assuming it's totally non-polar molecule, whereas this one is permanent dipoles and then a little bit of charge character as well. Happy? Cool.
Yeah.
We'll leave it there. I think like the next time we'll talk about maths. Okay, so we need to talk a bit about maths. I'll send you a maths. It's completely maths. It's got nothing to do with chemistry, but the maths is relevant in chemical context. You will see the relevance after you solve it, and then we can talk about it next time. Does that sound all right? Unfortunately for maths, you have to do. because you can't discuss through it. Only after you do and find the like differentiation or integration, then you'll be able to discuss the chemical context. Fair enough. It won't be long. It'll just be like one sheet problem set. But the fact that it's one sheet is not your usual A-level kind of thing. Yeah. No calculator. That's one. There's no calculator because in an interview you're not allowed to use calculator. And secondly, you should think about the problem, and instead of being like in an exam, you should think about the shortest possible way to get to the answer. Okay, it's not about like show all the steps, whatever. If you can rationalize how you get to the answer, that's good. That's great. Yeah. Okay. And it's not an exam. Just do what you can. And the first part is on trigonometry and some algebra. The second part, which is another time, will be on calculus, differentiation, and integration. Okay, cool. I know you don't do further maths. They might be one level above, but they should be doable. They're not that tricky. Okay, cool. Okay. So just text me when you have problems, and I hope you remember VSEPR, what we talked about today, you know, the sensible stuff. Okay?
Okay.
Any questions?
Not really. Actually, for A-levels, right?
You think about it, I mean, you got questions,
For, I'm not sure whether I should drop my physics.
There's a personal decision. Okay? If you think it's, when you think about it, people in the old days, there isn't this thing called drop because they did everything in one go. What I don't understand is you are essentially getting a second chance. Okay, you're getting a second chance to resit all the S, and without actually revising for S, it disadvantages you for A2 as well because A-level is a symbiotic thing. Everything is together. So in the interview, they can ask you a basic physics question. Next time we come to physical chem. In fact, after maths, then will be physical chem. Then you will see the more when I touch more on physics instead of the chemistry side. So inorganic is very much periodic table and that kind of thing, structure and bonding. But when you see physical chem, you will see the relevance of basic physics. I cannot give you advice. I mean, that's just up to you. Not up to other people, up to you.
Yeah, I think that's about it for now.
Okay, cool. If you got questions, just send me a text or something, okay? I'll send the problem set in a little bit. This time you should probably print out the problem set, do the maths, and if you can, take a picture and then send it to me. Preferably like, I don't know, I mean, if we meet up in a week, then send it to me a day before. If we meet up in 2 weeks, then send me to me the day before also. Okay?
All right.
Cool. Yeah. All right. All right.
Thank you, Chris.
Yeah. Okay. I'll send you the recording later on as well. Cool. Bye.